So welcome to the Synergy Software Package Architecture presentation. My name is Brandon Hussey. I'm a firmware engineer with Renesas. I'm based out of our Durham office, and I work full-time on Synergy. If you've been to DevCon before, you might recognize me. Last time I gave several labs on firmware integration technology, and I used to work on RX. So you'll see this slide over and over again. It's different places where you can engage with Renesas, all the way down from devices to full-blown solutions. Today we'll be talking about the SSP, which fits in at the platforms, right in the middle. So, the goal of this presentation is to show you that SSP was architected to accelerate your design. So let's look at some common problems that many of you have probably run into in the past with vendor-supplied software. One is sample code versus production code. You download some sample code from the vendor's website, and it's configured for one specific configuration on one board. Well, there's a problem there, and that's making the code work for your design. You have to go in there and modify it to make it work for your board and for what you really need. The problem's compounded when you start merging them, right? You're not using just one piece of sample code. More than likely, you're downloading multiple pieces and then trying to merge them all to work with your project. And many times, these different sample projects are done by different developers. So there might be no commonality between any of them, which makes it very difficult to merge them to work in your system. So, the goal of this presentation is to show you how SSP accelerates design and development and addresses these problems I just listed. So the agenda, I'm going to have some terms here, and it won't make sense now, but we'll go into each one. We'll start off with modules, interfaces, instances, the predefined layers of SSP, the layout and file structure, how we connect layers, and then some Q&A time. So first, a disclaimer. Lots of information is going to be covered in this presentation, and we don't have a whole lot of time. We have an hour. So if you have questions, if I can answer them very quickly and they're very short, then we can go ahead and answer them. Otherwise, I'm going to ask you to hold those questions and come ask me later. I'll be here all week. I'm also giving a lab on an intro to SSP later today and tomorrow. So if you're in there, you can feel free to talk to me. And also tonight, I'll be in the Meet the Experts at the exhibition hall. So I'll have my laptop and a big screen. So if you have questions, come ask me and we'll go in as much detail as you want to. But just for shortness of time, we might not be able to answer all your questions today. Also, this is very important. A complete understanding of SSP architecture is not required to use it. So, when I go through all this material today, a lot of you guys may like be scribbling down your notebooks, trying to get it all down. Because you're thinking, oh man, I got to remember all these structures and these pointers and doing all this and that and the other. That's not the case. We have E2 Studio, which takes care of almost all of it for you. So, I'm going to present it today, but you don't need to know all that to actually use it. But we're engineers. We want to know how stuff works, right? We don't want to take it for face value that it works. I want to know under the hood how the stuff works and how it hooks up. So that's what we're going to go over today. And finally, I will be showing some code in here in the lab, during the presentation on the slides. And many times that will be generated for you by E2 Studio. In the event that it's something that you would write in the user application, I denote it with a star like that. And you'll notice there won't be many cases of that. E2 Studio does an amazing amount of generation for you. All right, let's jump in. So here's the graphic pretty much everyone's seen in one form or another over the years. Right, you have an application up top, and then you have multiple blocks underneath it that build up all the support for it. And basically what this is saying is that we have blocks in there that can possibly be swapped in and out, and we can reuse them, which is great. That's a great thing to have. But the question is how do you actually enable that? How do you make that happen? How do we make sure those aren't really hard-coded and we can really reuse them and swap them out? Well, we'll talk about how we do that for SSP. And to do that, we need to start off with the very smallest piece, the module. So, the basics of a module. A module is the basic building block of SSP. Everything else is built upon a module. And they always have two concepts. One, they provide something upwards. If a module is not providing anything, then it should not be in your system. That means it's not doing anything. You don't add code that doesn't do anything for your project. Also, requires. This means that there might be some dependency underneath this module. Unless it's the very bottommost layer, there's probably going to be a dependency. So there's something that we say is that a module always provides, and often requires. So what are the contents of a module? What actually makes one up? Well, right now it's typically source code. And when I say source code, I mean source code with an API around it that you use to interact with it. We can provide anything we want to in a module, but today that's what they all are. They all provide source. And examples include driver code for peripherals. We're talking about code that actually touches the hardware registers and sets up the peripherals in a certain way that you need them to. Another example is the messaging framework. This is a more advanced module, and it's purely software. It uses RTOS objects, but it doesn't interact with any real hardware. Or Express Logic Xware, FileX, NetX, USBX, all of those are modules that we use inside of SSP. So there's a great variety of what can be supplied with a module. You may also hear the term component throughout the week. I just want to go ahead and clear up why you might hear that. And that is because inside of E2 Studio, or ISDE as we call it, when we deliver content, when we deliver module to your project, we do so through SYMSYS packs, which is an ARM standard. And inside the SYMSYS pack, when we package up a module, that's called a component inside a SYMSYS pack. So SYMSYS calls it a component, we call it a module. So interfaces, let's get into some of the good stuff. So here's a problem many of you have probably run into. We're going back to what we were talking about at the very beginning of the presentation with sample code. The user application will almost, usually, often differ from the supplied examples you get from the internet. So you get some provided sample code. Your application needs to communicate over I²C. So you download some code from the website, and it uses the SCI peripheral. If you're not familiar with the SCI from Renesas, that's our serial communications interface, and it's a peripheral that supports several serial interfaces. It supports UART, I²C, and Simple SPI. So the sample code uses the SCI peripheral to do I²C communications. But for your project, you don't want to use SCI. You want to use our more feature-rich IIC peripheral. So how do you do that? The problem or the issue here is that there's multiple modules that can supply the same functionality. And we need a way of supporting them without having to have n number of different app notes or sample codes available to you. So how do you handle those different implementations? Let's look at a couple ways you could do it. One is you could just swap the modules. So you remove the SCI module and replace it with the IIC module. So you just modify the code. And of course, there's some risk associated with that. Do the APIs match? Different developers may have done this. There's no guarantee these APIs match. So maybe some of the arguments needed for one of them is not provided or not in scope, so it's not easy to just do a search and replace. More importantly, does the functionality match? Let's take an example here where the provided sample code for the SCI is blocking, which means when you call that function, it's not going to return until the write is completed. Okay? Now we move to the IIC module, and it's non-blocking. That means when I call the function, it's going to return immediately, and that write is going to complete in the background. And then the application will check sometime later to see if the operation is completed. So if they work differently, then it's not going to be a simple search and replace once again. You have to add extra logic to your code to know how to handle this. And there's always the case where you can have copy and paste errors, right? You have to replace every instance of this, and you just get sloppy and you paste the wrong code in. Hopefully you get a compile error, but if you don't, that could be tricky to find. So that's not very optimal. Another option would be to support both of them. So you just modify all the places where you have the write, and you would have a conditional there to see whether you're using IIC or the SCI. Once again, many of you probably say, well, that's not very good either. You have to fix every location. You have to go to every single place and add a flag there to see which one you're using. There could be API parameter differences, just like I said on the last slide. So you have to make sure that you have all the information there for both APIs. And it's not future-proof. What if down the line you decide to use another peripheral, or maybe you want to, we have a new API that has more features you want to put in. That means you have to go back and modify every location again. And there's also going to be some performance degradation. Especially right now we have an if-else. If you decided to add another option in the future where you're going to go to an if-else if or a switch statement, no, it's not going to be very pretty. And the root problem here, as we see it, is that the application is required to know the underlying drivers. Here, the application wants to use I2C. I don't really care if it's on SCI or IIC. I might at some point, but really I just want to perform I2C communications. But instead of letting you focus on that, you're having to focus on the individual peripherals that we offer you. So how do we get around that? Interfaces. You can think of it at a high level as a contract between a module and its user. And one thing to remember that's very important is all modules adhere to an interface. And when we look at this diagram here that I showed earlier, whether it's implied or official, there is an agreement between each of these layers. Whenever there's an arrow going from one module to another, there's an agreement that that upper layer is going to get some functionality from the one below it. So instead of just letting it be implied, in SSP, we strictly define that as an interface. So let's look at them a little bit closer. It defines the contract. That's what an interface does. And it allows for modules to be interchanged. So we have our application here. And like I said, let's forget about the peripherals. What it wants to do is it wants to communicate over I2C. So what it does is it looks at the SSP I2C interface. Shown there on the left is little pieces of it, where it has certain functions, open, close, read, write. And it also has some different options. Options such as the mode. This would be typical of any I2C peripheral you ever use. It would have the mode. Is it fast mode plus, addressing, is it 7-bit, is it 10-bit mode, and the slave address. So then, once you've picked the interface, you can decide, okay, I want to use this interface. Now you have to decide whether it goes down to SCI or IIC. So what makes up an interface? Enumerations. And the stuff on the right here, you don't have to look at closely. It's just examples. We'll go into each one of these in a lot more detail in the future slides. So we have enumerations, structures. When it comes to structures, we have several special ones. A control structure, a configuration structure, an API structure, an instance structure. We have macros and type defs. So, enumerations, start off there. They provide stronger type checking. That's why we use them. Whenever you're filling out a structure member or a function argument and it's a type def, you know exactly what options are available. You can go look at the enumeration and see what members are there, and you know those are your potential options. And one really nice thing we do is all of our member names follow the type def name. This is part of our coding standard. So what's that mean and why is it helpful? Let's look at some examples here. This is the SPI interface, and these are two enumerations that we have. One is for the mode, and one's for the clock phase. So let's first look at the type def name. We have SPI_mode, and then SPI clock phase. The underscore T on the end is just our coding standard. We put underscore T on all type defs. So that's the name of the type def. Let's look at the members. Once again, it follows the same thing. It's just capitalized, SPI mode and SPI clock phase. So what this means is that it's very easy to see what enumerations are available for a type def. And using the autocomplete feature inside of E2 Studio, this makes it very easy to use. So the autocomplete will say, hey, I'm looking at a structure here, and I got to fill in the SPI mode member. What options are available to me? Typically, you would go to the header file, find that enumeration, see what options there are, and copy and paste. You don't have to do that inside of E2 Studio. What you can do is when you use autocomplete, you're going to see that the member you're filling in is of type SPI mode underscore T. So what you can start doing, you can just start typing in SPI mode. You just type in the type def. It doesn't have to be capitalized. So I type in SPI underscore mode, and then I hit Control Space, which activates autocomplete, and it's going to show me SPI mode master and SPI mode slave. I then just select it, hit enter, and it fills it in for me. So it makes development very easy and very quick. And if you're in our labs this week, you'll get to see that in action. So let's look at the instance structure. It encapsulates everything you need to use an interface. It's a very important point to get because we'll beat it in here as we keep on going on. So here's an example one from the UART interface. And there's a pointer to the control, a pointer to the configuration structure, and a pointer to the API structure. And the point I want you to remember is that when you use E2 Studio, it gives you a filled-in instance structure. And that's how you interact with the modules you're using. And the name of that structure is the name that you supply E2 Studio. Let's look at an example here. So you haven't seen this yet, you haven't had the labs, but you will. And this is where you can configure one of your modules. In this case, we're configuring an I2C module, and the name we give it right here is G_I2C. So when you hit generate, E2 Studio is going to generate code for you. And the part that's of most importance to you is this instance structure right here. And you can see it has the members filled in, and it gives it a name that you supplied. So in this case, it's G_I2C. Let's look into the individual pieces inside the instance structure. Let's first look at the control. And this helps you distinguish instances inside of a module. And the term we use here is module instances. So all SSP modules support multiple instances. If we have a UART driver, it's not going to support just channel 0. It's going to support all the channels on the device, which means that when you get into the code, somehow I have to know whether I'm working on channel 0, 1, 2, 3, etc. So one option would be just to pass in the channel number to all the APIs. And that works fine, mostly for drivers, but it does not work generically across all of our modules, especially when you get up to our framework layer, which we'll cover in a minute, and the number of instances there is only limited by the amount of memory you have. So to make that generic, we have a control structure. Here's an example of one for the I2C interface. And if you'll notice, the contents there are don't care. And the reason I say that is because the user allocates this structure, but they did not directly modify it. You pass it in to our module, it uses it, and then you get it back. The user should never be directly modifying the control structure. And it's similar to this or self in some other languages if you're familiar with that. And there's basically going to be one control instance. There's going to be one control per instance of a module. So going what I was just talking about, if you had 4 channels of UART, you're going to have 4 control structures, one for each channel. And all the functions take the pointer to the control as the first argument. So here's an example, once again, from the I2C interface. You can see all the functions. I have it highlighted in there in red. Take a pointer to the control as the first argument. Except for one. Can someone tell me which one doesn't take it? Raise a hand. Yes? That's right. You want a Snicker bar? You guys hand it back. I don't want to throw it back there. That's right. Version get does not take a pointer to the control structure. And the reason is because that returns the version of the module, which obviously does not depend on any instance. All right, let's look at the configuration structure. As the name implies, this is a configuration for the interface. And it's only used in the open. As you saw earlier, every open takes a pointer to the control and a pointer to the configuration structure. Here's an example from I2C. We've been using it. And you'll see there some members that you probably recognize: channel, the rate, slave address, address mode. There's several common configuration members I want to point out and go through. And this is probably going to be common in almost all the modules you use, especially at the driver layer. And that's the callback, the context, and the extension, the pextend. Let's look at more of those in detail. So callbacks. So callbacks alert users to a module event. So like I was talking about earlier, about blocking and non-blocking, almost all SSP modules, in fact I believe all of them, are all non-blocking, which means you're going to start an operation, it's going to return immediately to the user, and you can continue doing work while the operation finishes in the background. Now, with that being the case, the application has to have some way of knowing that the operation completed. How do you do that? Well, you could have a function you call, status get, something like that, but that's not very efficient because you're basically polling. So what we use, we have callbacks. So in your application, in your user code, you will write a function, a callback function. Then when you call open for this module, you're going to provide a pointer to that function. So then when the event occurs, we call that function to let you know, and you can do what you need. Now you're going to be inside of an interrupt service routine, so keep it short. Context, these are used together, is similar to passing arguments to a callback. So let's look at an example of how that's used. So basically context allows users to pass what they need to a callback. So an SSP module handles the interrupt. So we call the callback function. So we can pass what we want to the callback function, but we do not know what you need in the callback function. So there needs to be some way for users to pass what they need to the callback. So let's look at an example here. We have an application calling an SSP function. and it calls the open, and in that open, there's a pointer to the context. So it's provided there. Now the SSP module has that stored. An interrupt fires at some point, in which case the callback function is called. When that callback function is called, the context pointer is sent back to the user. So in essence, what it really looks like is the application is passing the context to itself. It's almost like calling a function. Let's look at an example. So one of the great features about having a callback in context is that it allows for a common user callback function. So here's an example. We have two channels of SPI. So this could be on the same SPI peripheral, could not. So we have two callbacks here, right? We have one for SPI channel 0, one for SPI channel 1. And what we're doing here is we're setting a flag to indicate to the application that our last transfer has completed. So that means the application will be sitting there waiting for this flag to change. Well, how can we make this common? Because right now it's hard set. If we added another channel, we have to add another callback. Well, here's an example. If you notice, here's the blue star. This is one of the few cases of where this is code that you would write. So we started off, we had these two flags that we're setting to true. But once again, if this ever changes, you have to change it here as well. So instead, what we want to do is we want to get a pointer to that flag or get the flag from the context. So what we did is we created a user struct type. It's just some structure, and it has the flag inside of it. When we call the open, we pass that in as the context. So now when this callback gets called, we can get that structure back, as I have shown there on the right. So the structure P data, we're casting it from the context. Now, I can set that flag to true right there. So this will work for unlimited number of channels, and it'll work across peripherals too. Let's say you're using our SPI peripheral and the SCI and Simple SPI. You could use the same callback to span peripherals. It does not matter. So this is flexible and scalable. So the API structure, and pretty clear, this is the functions available for this interface. So it is shown there. We have open, close, read, write, and then a couple other ones. This defines the runtime behavior of your system. This is how you interact with modules at runtime. These are the functions available. And all functions are accessed to an instance of the structure. This is very important. When you use our modules, you're not going to make direct function calls to r_sci_write, as I showed earlier. When you do that, you're directly tying your application to the SCI peripheral and the SCI module. Excuse me. We don't want to do that. We want to be able to swap them out. So instead, you're going to be going through an API structure, as we've shown here. And I have some examples of that coming up. Now, when you're looking at this structure here, this means this is all the functions available. So individual instances, as we'll go in a minute, do not add extra functions. If you add extra functions outside of this table and use it, then you've now directly tied yourself to a particular peripheral or module. So let's look at swapping modules using interfaces. So the only thing you have to do is swap out the instance pointer. So remember, back at the very beginning of this, we looked at two ways of swapping out sample code and moving to what you needed. We looked at replacing and then supporting both. Let's look at how we do it with SSP. So once again, as a reminder, here's what the instance structure looks like. There's a pointer in there to the control structure, the configuration structure, and the API structure. And then beneath there, we're declaring one P_I2C. It's a pointer we're using. So the application, once again, cares about I²C. So when it looks for a write, this is how it's going to do it. It's going to go into the P_I2C. It's going to get the API, and then it's going to call the write. Now, where does that go down to? Does that go down to SCI or IIC? I don't know. It depends on where the P_I2C is pointing to. So here it is. If we wanted it to go down to SCI, then we set it to, this is just an example name that you would provide in the ISD. I'm setting it to G_my_I2C on SCI. All right, so that's one example you have. Let's go back to what we were talking about. We want to move to IIC. To move that sample code from SCI to IIC, the only thing we have to do is change that pointer like that. All the rest of your application code remains the same. So the benefits, users need to understand the interface, not each specific instance. We were talking about before. Now you can focus on knowing that, hey, I need to use I²C, and Renesas offers these peripherals that implement that. You don't have to worry about reading the 100-page guide for that peripheral. You can easily add new variations in the future. This is addressing the future-proof issue. So this is the example I gave on the last slide. where we have support for the SCI and simple I2C mode and the IIC peripheral. Let's say generation 2 comes around. We add this brand new I2C peripheral that supports an even faster bit rate. So the only code modification required on your end is changing that pointer. So we add a new module called IIC max, and you just change that P_I2C pointer to now point to my I2C on IIC max. All of your application code remains the same. All right, so that's the interfaces. So let's look into instances. I've talked about this a couple of times. So interfaces do not provide code. Interfaces are that contract we talked about. It's just a header file that defines the rules. Where's the code actually implemented at? That's an instance. Instances implement an interface. So, using the example we've been using, we have the I2C interface. It is implemented by SCI in simple I2C mode, and it is also implemented by the IIC module. So, one question you probably all have is, Module X has this great feature that is not exposed by interface Y. That's what I'm talking about. So let's talk about the I2C interface. On the SCI peripheral, it runs up to 400 kilohertz. It's fast mode. But our IIC peripheral goes up to 1 megahertz. It's fast mode plus. So how do we support both of those? Well, in this case, I2C interface would have an enumeration for the mode, and it would have options for fast mode and fast mode plus. So that means that you would be able to set fast mode plus for SCI, but of course when you send in the open, it would return an error saying not supported. Now to make that easier, when you go into E2 Studio, when you pick one of these instances, it knows what's supported. So if you pick SCI for I2C, it's not going to show you fast mode plus as an option. It's only going to show you fast mode. So you'd only run into that issue if you're doing the code manually. So look at another example, SPI. So when it comes to SPI, we also have SCI in simple SPI mode, and it provides nothing additional to the interface. The interface encapsulates all the functionality provided in the SCI and simple SPI mode. But we also have a SPI peripheral, and it has many configurable settings, many that many people may never use, but they're there, and some people may want to use them. So how do we expose those? Because we don't want to say you just can't use them. So we have interface extensions. So instances can extend the functionality of an interface. So here's an interface, this is a generic one. Every single interface has this, and you'll see at the bottom, void star p_extend. This is the extension pointer. What goes in there? Well, it's defined by the instance. It's very important, right? Extensions are not inside the interface. They're pointed to by the interface, but they're defined in the instance. And what are they made up of? Well, you can see it over there. It's a structure, and it's called interface, whatever the interface is, on instance. And inside of there, you'll see some members you can put in there. So what kind of information can you put in there? It's a structure. Once again, going back to what I talked about before, an extension is just a structure with data. So it's going to have extra configuration information for this module. You will not be providing, there will not be extra API functions in here. If we provide extra API functions, then we're breaking the interface because only this module will support that API call. But you can provide other information to configure the module in this extension. So let's look at an example. You actually see this in the labs. So here we have the GPT, which is our general PWM timer. It's a very powerful timer. And it implements the timer interface. So you can see the options there, pretty standard. We also have another timer called the AGT, which is the asynchronous general purpose timer. And it's shown there. You'll notice there's a lot of similarities between the two. But then there's two blocks where it's different. This piece and this piece. So this is the extension to the timer interface that these timers provide. So on the AGT side, the first one there is clock or count source. So the AGT can actually count on a variety of different clocks, while the GPT cannot. So instead of putting that in the generic interface, that goes in the extension for the AGT. So one very nice thing about it is, like I just mentioned earlier, inside of E2 Studio, it knows about the extension for an interface. So it presents it to you right in line with the other interface options. All right, let's look at using an instance of an interface. This is very important. So once again, inside of our instance structure, you're going to find 3 pointers. A pointer to the control, a pointer to the configuration, and a pointer to the API structure. So you'll notice in there was not the extension we just talked about. Where's the extension at? It's pointed to by the pextend member inside of the configuration structure. So that's where it's at, even though it's not directly shown in the instance structure. So this is inside of E2 Studio. We're configuring a SPI module, and we're giving it the name G_SPI. Like I said, that's very important. You always need to remember the name you gave it, because that's how you're going to use the interface. So here's the prototype for the open function. We're going to call open, and there's a blue star there, so we're starting to use this is being the user space. We always start with the name. If you don't know what to write, you write the name. So the name is G_SPI, so I write G_SPI. I put a period for the structure. The autocomplete feature of E2 Studio will then be automatically triggered, or you can hit control space, and it's going to show you the options inside of that structure. So you're going to see a pointer to the control, a pointer to the configuration, and a pointer to the API. We're wanting to call the open, so I'm going to guess anytime I make a function call, it's going through the API structure. So I put in PAPI, and I get the open. Now I'm ready to fill in the rest of the arguments. So I look at the prototype, and I see it takes a pointer to the control. How am I going to get access to the control? Someone. What am I going to type now? Someone raise your hand. G_SPI, great. Which, you want a shirt? Sure. White or blue? You got the only one. Right, so we type in G_SPI and we put the period there. We're going to notice there's a pointer to the control structure. Great. All right, so now we look and we have one more argument. It's a pointer to the configuration structure. So we move to there. All right, someone raise your hand. What are you going to type? Very good. You want a shirt? Right, so you go to G_SPI, and this time you'll find a pointer to the configuration structure. Notice everything went through the instance structure. It is named what you named it inside of E2 Studio. This makes it very easy to use. So now we'll say we're going to use the read and write. Once again, we do the same thing. Now the period's there because once you get to the read and write, then it's going to be application-specific stuff in there. You know, read buffer address, number of bytes, stuff like that. Let's look at the predefined layers of SSP. So at the very bottom, we have the microcontroller. Above that's the BSP, our board support package. Above that's the driver layer and the framework. So those are generic terms. So we'll look into more detail what these layers actually mean. The BSP is the foundation for SSP. If you remember at the very beginning of this presentation, I was talking about one of the problems you have with vendor code is merging them together. If you have 3 pieces of sample code and there's no common piece to it, it makes them very hard to merge. So the BSP is the foundation of every SSP project. You'll always have one. And it's required. And what does it handle for you? Clocks. The Synergy MCUs have a pretty advanced clock tree, so it handles all of that for you. Stacks, your MSP, your PSP, and also your heap. The C runtime environment. Interrupts. I don't have enough time to explain it here, but Synergy has a very flexible, very advanced interrupt configuration, and it takes care of all of that for you. And also pin configuration. Inside of E2 Studio, we have a graphical pin configurator which exports data table that's used by the BSP. Now, that's one thing I want to talk about with the BSP. It's entirely data-driven. So the BSP code on the inside doesn't have to change. The structures you pass in to configure it are what change. And that's all given to you or all generated for you by the ISD. Let's move up to the driver layer. These access the MCU registers directly. And it provides a low level of hardware abstraction, not much more than what the peripheral offers. They are RTOS aware, but they do not use RTOS services. This means that they can be used in a project with RTOS or without. And they're easy to notice because all of their names begin with R_. And examples include, we've been talking about them already, SPI, I2C, or ADC. All right, let's move to the framework layer. This is where it gets more interesting, more fun. So these can use RTOS objects, and they very often do use RTOS objects. And it provides a higher level of abstraction. So this is where you're getting more features for your application. And they typically use the driver layer for interacting with hardware. If I needed to communicate over SPI, I'm not going to do it from the framework layer. I'm going to go through the driver layer. And they're easy to find because all the module names begin with SF underscore. And examples include our SPI I2C bus framework. So let's quickly take a look at that. So at the very top there, we have several devices that are on some bus. What we're doing here is we're abstracting those devices. So typically you might say, well, I have an accelerometer on I2C channel 1. Well, what we're going to say now is you just have an accelerometer, and it has to be on some bus. What bus? I don't really know right now. So you define the devices. What's the information that's specific to that device? Then we define a more abstract bus. So this bus has information about what it's actually implemented on, what peripheral, what channel. So then we tie that device to the bus. So the device doesn't really know anything about what bus it's actually on. It just knows that it's on a particular bus. We also offer a thread monitor. So we have 3 threads here, and they're all running, and we want to make sure that they continue to run, that there's no deadlock, they don't get stuck in a while one loop. So what we do is there's a monitor. And what happens is these threads check in with that monitor every so often. If a thread doesn't check in with that monitor and the period goes by, then he uses the watchdog interface and he can reset your MCU. So these are just 2 examples of some of the framework modules that we provide. So what is possible? So I showed you earlier, it looks like it always goes straight down, right? Framework, driver, BSP, MCU. Well, what's really possible with the SSP? Are you limited to that? So we have the MCU at the bottom. We have the BSP as shown. We have the driver, which can go through the BSP or can go directly to the MCU. Same thing for framework. So the framework might go directly to the MCU. Why would it do that? Well, the problem is that sometimes we need special drivers. Motor control, for example. If you're doing a motor control, you might need to use multiple channels of our GPT timer peripheral, and you might need to use like DTC with it as well. So to do that, we're not going to be able to do that by integrating multiple generic interfaces. Instead, we need those tightly coupled and very efficient, and we can do that in one framework module. So that is possible. And the same thing applies for the user application. Typically, you're going to work at the highest level, whether it's framework or driver. But, of course, you're going to have to write your own custom drivers too, right, for doing whatever special function you need for your application. So you can access the MCU directly as well. Nothing's limiting you from that. Let's look at the layout and file structure quickly. And there's a lot of information on here. What we really want to show you is the symmetry between our file structure. So at the very top, we have the SSP. And when you get your 1.0 beta, you'll notice that the SSP directory is actually underneath another directory called Synergy. Then underneath there, we have 3 folders. We have 2. We have include and source, and then the SSP configuration directory is off to the side. Underneath there, you'll see a lot of symmetry between all of these. So we start off, they all have BSP directories. Underneath the include, you'll find that we have interface and instance header directories, the API and instance. And then same thing for the framework. They all have framework directories, and then there's separate interface and instance directories in the include. Let's look at connecting layers. So just like we were talking about earlier, when you're using an interface, modules do the same thing when they have requirements. They have an instance structure pointer. So let's look at an example here. This is the framework external IRQ. And it requires a driver level external IRQ. This is for a pin interrupt. So how does it use that? How does it actually go through using that lower level driver module? Well, if you look at its configuration structure, there's a pointer in there to the lower level instance structure. So just like you were using in that previous slide, modules that require other ones use that structure as well. And E2 Studio does this for you. It makes all those ties for you when you create these different layers inside. It actually provides extra features. They actually do error checking to make sure that you have them set up correctly. And you'll see that in the labs. So there's a problem here, and the problem is that some interfaces will not know possible lower level requirements. What do I mean by that? Let's look at an example, FileX. FileX maps down to our block media interface inside of SSP. The block media is very generic. It basically says open, close, read, write. So we can go down to any number of different interfaces. Some examples would be USB mass storage, SPI flash, or SDMMC. So that being the case, how do we support that? Do we put the instance structure pointers for USB mass storage, SPI flash, and SDMMC inside the block media interface? No, that would be confusing. There'll be many of them in there, it'd be bloated, it'd have to change often. So instead what we do is we have a pointer to the instance structure that goes in the instance extension. So there's the instance extension for SDMMC. You can see there it's block media on SDMMC, and there's a pointer to the instance structure in there. So that's how we handle that when there's interfaces that are generic. Excuse me, generic. All right, summary. So general usage, you select an interface and an instance. You start off picking what interface you want to use, and then you can pick an instance. And E2 Studio guides you on this. It helps you pick an instance for your interface. You then allocate control and configuration structures. Guess what? E2 Studio does this for you. You then access the API functions through an API pointer in the instance structure. Guess what? E2 Studio helps you do this. It creates the instance structure for you and gives it a name that you provide. And here's an example, as we go through before. This time it's for ADC instance. And then you can refer to the documents and references. We do use Doxygen for our documentation, and that's provided with the SSP. And if you're in my intro to SSP lab, we go through and look at it quickly. All right, let's quickly go back through the terms that we used during the lecture. The module is a software unit that enables a block of functionality. The BSP module is the foundation solution, and it takes you from reset to main. Driver modules provide a low level of hardware abstraction. There's no RTOS. They are RTOS aware. And each forms a piece of our hardware abstraction layer. For the framework modules, a higher level of abstraction, they can and often do use the RTOS. And each one of these forms a piece of the application framework. Interface, it's a contract that modules follow to define functionality. The instance structure has everything you need to use an interface. We then have an interface instance, and that's a module that implements a given interface. So going back to our example, for the I2C interface, we had two instances. We had SCI and IIC. The module API is the API associated with it, and that is common to all instances of a module. If we have 4 channels of UART, they're all going to have the same API. All right, let's look at a module instance. This is an allocated object of a given module type. The module instance control structure is the private memory for that allocated object. And the module instance configuration structure is the configuration data for that module instance. So while the API is common across all instances of a module, the control and configuration are specific to each one. You have a callback function, which alerts the user to module events, and you can pass data to that using the context. Then we have an extension structure, which provides instance-specific configuration data. It's very important, instance-specific. So in summary, we covered modules, interfaces, instances, the predefined layers of SSP, the layout and file structure, connecting layers, and we have some Q&A, we'll get there. So let's go back to the original problem. So some of the common limitations that you find, you have sample code versus production code. And we had to make the code work for your design. We had to make changes, use different peripherals, use different configurations. And then there's difficulties in merging. So I hope through this presentation you saw that we can address these with SSP. And that SSP will accelerate your development, allowing you to innovate by providing well-architected code that was made to be built upon. And graphical tools that make building and configuration of the projects easy. You might think there's a lot of complexity in there, but E2 Studio takes care of all of that for you. And it just presents to you that instance structure that you can use. All right, we actually have a little bit of time for questions. It is 2:05. Anybody? We have a microphone coming to you so we can record it.
I've done several RX projects using the Micrium.
Okay.
And there's always, at the API level, confusion in that there's 3 ways to open a file. They support different ANSI standards or whatever for opening files. Or in TCP/IP, you can call blocking functions or not blocking functions to read a block. Does SSP reduce my my options so I can't make errors of omission.
Yeah, that's a good point. And generally, SSP only provides one function for each functionality. So we have one open, we have one close. We typically have one read and one write. So thanks for asking a question. You get the last shirt if you want it.
I've already got one.
You already got one? Okay. Who wants to ask another question and get a t-shirt?
You mentioned the framework can and often does use RTOS.
That's correct.
So to use SSP, do you need to use an RTOS?
No. Very good question. So, do you have to use RTOS to use SSP? No, you do not. So, if you're not using an RTOS, you can definitely always use up to the driver layer. Because driver layers are RTOS aware, which means that they won't interfere with the RTOS, but they do not use RTOS objects. Now, if you move up to the framework layer, more than likely you're going to have an RTOS. There might be a couple of modules that do not use RTOS, but by and large, most of them do. So that's basically the cutting point. If you're using up to the driver layer, then you're not required to have an RTOS. Above that, most likely.
Brandon, one question.
Yep.
Are you forced to use FedEx, or can you use maybe any of the other options?
So his question was, if you're using a RTOS, are you forced to use ThreadX, or there are other options? And yes, if you're using SSP, we do use ThreadX directly. So there's no option for swapping it out. Yep.
If I'm using ThreadX, can I make direct calls to ThreadX API, or do I have to go through a framework?
Very good question. No, you can use ThreadX directly. There's no indirection or any layer in between. You can make ThreadX calls directly. So his question was, is that true for GUIX, NetX? Yes, that's true. That's a good question. You want the t-shirt? You're way far in the back, so there's no way I'm going to be able to throw it back there.
Yeah.
Oh, you're good. Any other questions? Yes?
So with all your predefined interfaces and your callbacks and all that, if you have real hard embedded requirements in terms of timing, do you document what the latencies are of all these, and how do you control like interrupt latencies and interactions and priorities and things like that to give you that real hard control?
That's a good point. So there's different options there. One, we do provide latencies in some of our documentation. We're still working on that, so you're not going to see it in our documentation yet. When it comes to priorities, all the priorities are defined by the user through the graphical user interface. So that's up to you to define the priorities in your system. Now, let's say that for some reason, SSP is not going to be able to provide the response time you need. You can work outside of SSP, just like I showed in that diagram with the application going directly down. I'm not saying this is going to be a typical case, but if there is some hard requirement that you have to meet, and SSP is not going to meet, then yes, you can go directly to the hardware yourself. And we can assist you with doing that too, making a new SSP module for you. Any other questions? Just wait a second. He's going to get you the microphone so we can record it.
Is SSP the thread safe and re-entrant?
That's right. So if you're working at the framework level, then we use RTOS services and we are thread safe. Any other questions? Yep. One second. Making them run back and forth from the front to the back.
Say in a UART, you have an RS-485, and you have to toggle the transmit and receive line on the chip. And you have the BSP board support package that's built by SSP. Where do we get access at that point to toggle our transmit and receive line?
So that's a good question to bring up. You're talking about the SSP or building the BSP. So when we're talking about the BSP, SSP provides BSPs for every single one of the boards that we provide. When you go to production, when you go into your design, you're going to create your own BSP. So you can put whatever you want to in there. So if you need references to those pins, you can do that. And what we do is we provide a tool that's up in the gallery now to help you create a custom BSP. So it's a command line tool currently. What happens is you tell it what BSP you want to base your design off of, one of our existing ones. You create a new one, you can customize it. And once you do that, the great thing is you can use your custom BSP, your name, your settings, in E2 Studio, just like you would one of our BSPs. So you can configure it all graphically, use all the same tools that we have. Okay. Any other questions? All right, like I said, I have 2 labs So I'll be there, and I'll also be at Meet the Experts tonight. So I know some of you have some probably deeper questions you want to ask me. Please come up, talk to us about it. We're very interested in getting feedback. And if you will, please go to the app and fill out the survey for this presentation. And thanks for coming, guys.